Good afternoon. Welcome to You Digitized It, Now What? My name is Amanda Whitmire. I am the head librarian at Stanford's Marine Biology Library. I'm coming to you today from the west coast of the United States. One of the things that drives my digital collections work is the reality that there is a lack of ecologically relevant observational data in marine environments, and my feeling that marine field stations and libraries like mine are in a position to help ameliorate these observational gaps. My talk today is focused on some recent explorations and computational approaches to creating biodiversity datasets from library collections. I'd like to explore the issue of a lack of adequate data by taking a quick look at one of the largest biodiversity catalogs in the world, GBIF. One of the most valuable things about GBIF is its collections of species occurrence data, which say, I saw this thing at this place at this time. If we take a look at a very common anemone found in the tide pools at Hopkins Marine Station, we get a sense of its geographic range and see that there are 2,468 occurrences. That seems like a lot. But if we look one step deeper at the occurrence data for Anthopleura, what we find is that observations are heavily skewed toward the last decade or so. This doesn't mean that there are zero observations back in time. Notice the bump in the 1970s, but there are significant observational gaps. In fact, if you look at the temporal record for all species occurrences in GBIF, you see the same trend. A lack of historical species data, even in recent history, is very real. In many cases, marine stations have been in any given spot for a long time. For example, Hopkins Marine Station was established in 1892, and we've been at our current site for over 100 years. Here I'm showing just one time series collection that we have, undergraduate student research papers, which are actually very common at marine stations along the entire coast of Western North America. When scientists speak of a need for data over time and space scales that are suitable for addressing ecological questions, I see great potential in text mining across these locations and collections. So I'd like to spend the next few minutes sharing some tools and approaches to text mining that can extract and enhance biodiversity data that may be hidden in legacy text collections. As an example, I'm going to use a student paper from Hopkins Marine Station that I clicked on randomly in my files. Temporal and spatial activity patterns of the intertidal chitin Mopalia muscosa, and this is from 1974. Keeping in mind our example from GBIF, one thing that we're really interested in finding is species occurrences. In this example, the start of the methods section offers an excellent candidate. Notice that there is a date, a location, and a taxonomic name. Now, a human can read this very quickly and decide whether this sentence or paragraph constitute a species occurrence. But how could you find this taxonomic name and make this assessment using computational methods? One tool that I highly recommend is Global Names Finder, which is one resource from a nice set of taxonomic tools from Global Names Architecture. This is an open source tool that you can use in a web browser, very handy for checking things real quick, or in a terminal window or in R or Python, and there's also an API. Here you can see that in our chitin paper example, GNFinder found 35 unique taxonomic names and 61 names total, because some are mentioned more than once. GNFinder will give you results in several formats. This is an example of JSON. The first thing I want to highlight is that GNFinder can find matches for misspelled or partial taxonomic names, which is really helpful if you're working with OCR results. In this example, I ran GNFinder against 445 student papers and found 10,622 taxonomic names in those papers. You can see the breakdown of matches, 70% of which were exact. 185 were fuzzy, meaning there was probably a misspelling or a transcription error. 25% of the matches were classified as no match, which seems weird to include. But if you look at the no match results, what you find is that the large majority are the abbreviated binomial names. Where species occurrence names are matched exactly, like in this example, GNFinder provides an identifier and a link to the authority source it used for the match, in this case, the Catalog of Life. If you pop on over to Catalog of Life, you'll see much more taxonomic information about your species, including vernacular names, synonyms, Bayesianims, the full classification, and so on. There's also a link out to the resource that Catalog of Life is using as its authority, in this case, Molluscabase for worms. Once you have a confirmed species name, there are APIs for several taxonomic resources. Here we see the Wikidata and Wikipedia pages for Mopalia muscosa. These pages have descriptive information and link out to photographs, references, and other taxonomic identifiers that exist in what some folks refer to as the biodiversity knowledge graph. There's an API for GBIF, of course, which allows you to connect to species occurrence data, more data sites, and taxonomic checklists. So here's an overview of what I just described, just a few of the many tools and resources that are available to connect with and pull from in the online network of connected biodiversity resources. I want to emphasize, especially for the librarians and data curators out there, how important just this first step in the process is. If you have a set of resources, student papers, research reports, anything like that in your catalog or database, the ability to add verified taxonomic names to your metadata record is a huge asset to researchers who might be looking for them in your collections. So if all you do is use GNFinder to find taxonomic names to add, that's a big deal. For those of you who, like me, want to go to the next step and find occurrence records, it really is a whole other challenge. For example, back to our chitin paper. Recall the tidy species occurrence in the methods section and compare that with the references section from the same paper. How does the machine know the difference between what's on the left and what's on the right if all you're asking it to do is find a date, a taxonomic name, and a place? Well, we need to help the machine by asking a more specific question. And this is where this talk gets into an area of active development for me and my collaborators. We're exploring the use of named entity recognition and other natural language processing tools. In the example above, we're using Spacie to identify their out-of-the-box entities for dates, events, locations, and geopolitical entities, as well as adding a custom entity pipeline for taxonomic names that we've scraped from the student papers. It turns out that finding the words we're interested in is relatively easy, and we're back to the problem of being able to sift through every possible taxonomic name and find good candidates for occurrence records. I see at least a couple of ways to try this. One, we could just ask Spacie to show us sentences or paragraphs where a location occurs within 5 or 10 words of species. I've seen in student papers that they don't always include a specific date because the year of the observation is implied by the year the student conducted the research. This is a simple approach that just doesn't involve natural language modeling at all. Another approach to filtering out false positives might be to train Spacie's linguistic model to look for entities and the relationships between them. There is an annotation tool called Prodigy that was built for just the task, among other things, and we're definitely going to give that a try. We've gotten started on an interface that would allow us to view potential species occurrence candidates and accept or reject them. This is built as a Streamlit app, which is yet another tool from the team who created Spacie and Prodigy. Streamlit helps you create web apps from Python scripts, and we're still refining the look and feel and functionality of this app. But this is the kind of tool that I'm very interested in developing to help librarians and other data curators in sifting through large text collections of historical observational work. So that was just a very short tour of our explorations and computational approaches to creating and enhancing biodiversity datasets from library collections. It's relatively early days for this work, but I see a lot of potential, and I'm excited to move this forward. I've been tinkering around with library collections and text mining and biodiversity for a couple of years now, and many people have been generous in their collaborations with me. I thank all of them, and I thank you for your time.